Hi again. So today we're going to continue Chapter 3, Section 7, and we're going to discuss heating and cooling curves. So down below is a heating curve. And this is specifically for water. So you'll notice we have a y-axis and an x-axis. On the x-axis is heat added. So imagine we have a bucket of ice and it's sitting on a hot plate and we're just letting it heat up. So initially we have our ice and we add heat to increase the temperature of the ice until it reaches its melting point. Now you'll notice that initially we had a diagonal line. That's showing the increase in temperature for the solid state of water. And then once we hit the melting point, now we have a horizontal line. So that's showing a change of state. And we can keep going. So once everything has melted, we'll have a liquid and we'll increase its temperature by adding heat until we reach the boiling point. And then we have another change of state, which is horizontal. And then finally we have our gas. So again, diagonal lines on our heating curve indicate changes in temperature for a physical state. And horizontal lines or plateaus indicate changes of state. Now let's actually draw this out in more detail. Okay. So again, for the heating curve for water, we have our y-axis and our x-axis. And the x-axis is heat added. And the y-axis is the temperature in degrees Celsius. Now, of course, you could use other temperature scales, but just for convenience, we're going to use degrees Celsius. Okay, so let's say initially we're starting at a negative temperature. So let's say -4 degrees Celsius. And then that means we have ice, because we have solid water below 0 degrees Celsius. All right, so we add some heat and the temperature will increase for our solid until we hit the melting point, which is 0 degrees Celsius. And at that point, all of the heat that we're adding to our ice is no longer going into the temperature of ice. It's actually going to melt the ice. All right. Now, once everything has melted, then we have a liquid. And that liquid is going to increase in temperature as we add heat. So we'll have another diagonal line until we hit the boiling point of water, which is 100 degrees Celsius. And at that point, again, any heat that's added is going into the energy of the particles. So the liquid particles are now going to gain more energy to become a gas. And the change of state there is the process of boiling. All right, and then we'll have our gas, which can also increase in temperature if we add more heat. Now, remember from our last video that we also talked about specific heat. So for each state of matter here, we have a different specific heat value. So the solid has its own specific heat. The liquid has its own specific heat. And the gas has its own specific heat. And then we also talked about a heat of fusion and a heat of vaporization. So the heat of fusion is the amount of heat needed to melt ice or, some other substances solid. So we'll write heat of fusion above melting here. And then the heat of vaporization is associated with boiling. All right. So let's say, for instance, we wanted to figure out how much heat we have to add to 20 grams of ice in order to melt it and then boil it. We would need different equations for each step of this heating curve. So let's go through that. All right, so step 1, we need to calculate or determine the heat needed to increase the temperature of the solid. So also remember from our last video that we saw an equation where heat is equal to mass times a change in temperature times specific heat. And we'll add solid to the specific heat there. Okay, so then all we would have to do is plug in the mass of the ice that we have, the change in the temperature, and its specific heat value, which we would look up in a table. Now, what if we then wanted to calculate how much heat is needed to melt the ice? And I'll just write solid here because this could also apply to other substances other than water. So then we would use this equation, which we also saw in the last video, where we multiply the mass by the heat of fusion. All right, so now let's say we melt our solid and now we have a liquid, and we want to determine how much heat is needed to increase the temperature of the liquid. So heat needed to increase temperature of liquid. So now we're going to go back to our first equation. So mass times change in temperature times specific heat. But this time we're going to use the specific heat of the liquid, and the temperature change might be different as well. Now let's say we have our liquid and we increase its temperature to the boiling point, and we want to determine how much heat is needed to boil the liquid. So now we're going to use an equation where we multiply the mass of the liquid by the heat of vaporization. So this is similar to the equation in step 2, except instead of a heat of fusion, we're going to use a heat of vaporization. And that's something we can look up in a table or online by a trusted source. All right, and then let's say we boil all of our liquid and then we increase the temperature of the gas. How much heat is needed to increase the temperature of the gas? So we're going to go back to our first equation again, but this time we're going to need the specific heat of the gas. So we would have to look that up in a table. Okay, so these are the 5 equations that you need in order, to calculate the heat of a solid as it increases in temperature, as it melts, and then as we increase the temperature of the liquid, and then as we boil the liquid, and then as we increase the temperature of a gas. Now, sometimes you might just need to determine steps 2 and 3, or steps 2, 3, and 4. And that's okay. You can kind of go through this chart and figure out which equations you need for each step. All right. So let's go through a learning check real quick. So number 1, a plateau or horizontal line on a heating curve represents A, a temperature change, B, a constant temperature, or C, a change of state. And I'll give you a hint, there might be more than one right answer. So we said that a plateau or horizontal line represents a constant temperature, but it also represents a change of state. And what about 2? A sloped line on a heating curve represents a temperature change, a constant temperature, or a change of state. So we said that a sloped line represents a temperature change. All right, so I also wanted to go back to our heating curve. So I'm going to go back a couple slides here. Now, what if we're going in the opposite direction? So what if we start with a gas and then we turn it into a liquid? That means we're removing heat, right? And remember, we talked about the opposite process of boiling is condensation. And then what if we cool down our liquid and turn it into a solid? That's called freezing. So if we're going in the opposite direction from gas to liquid to solid, that would be called a cooling curve. So actually, I'm going to skip this learning curve there. So a cooling curve is almost the mirror image of a heating curve. So this illustrates the change in temperatures and changes of state as heat is removed. So this time we start with steam, and then it condenses into liquid or water, and eventually we freeze it and it turns into ice. So during condensation or boiling, we do have 2 phases present there, or 2 states of matter. We have both water and steam. So if you've ever boiled a liquid, you know that gas starts to form, but you still have some liquid left. And then during the process of freezing or melting, we have water and ice present. So if you've ever watched ice melt on a surface, you have the solid there, but you also start to see some liquid form. So just something to keep in mind. So now let's do a practice problem where we combine heat calculations. So in this problem, we're not going to consider water, we're going to consider a different substance, ethanol. And ethanol is what's found in your gas. They do add some ethanol to it. It's also found in alcoholic beverages. So this is a pretty common substance. So let's calculate the total heat in joules needed to convert 15 grams of liquid ethanol at 25 degrees Celsius to a gas at its boiling point of 78 degrees Celsius. So ethanol has a specific heat of 2.46 joules per gram degree Celsius and a heat of vaporization of 841 joules per gram. Whew, okay, that's a lot of information. So we're given the mass. Great. We're also given a temperature change, 78 and 25, so we'll need to probably find the difference there. And we're also given the specific heat of liquid ethanol and the heat of vaporization. Okay, so really what we're trying to figure out here is how much heat is needed to increase the temperature of the liquid and then boil it. So let's actually draw a picture to kind of help us visualize this. All right, so I'm going to draw our heating curve. All right, so we were told that we're starting with a liquid and we're increasing its temperature. So I'm just going to draw that part. And then we're also told that we're going to boil the liquid. So I'll show that part as well. Okay. Now, we were told that the initial temperature of our liquid is 25 degrees Celsius, so maybe that's here. Doesn't really matter as long as it's somewhere in the liquid range. And then we were also told that the boiling point of ethanol is 78 degrees Celsius. Okay, so we have two steps here. We're going to increase the temperature of the liquid, and then we're going to boil the liquid. So we can write out our steps here. So we need to calculate the heat needed to increase the temperature of the liquid. And then 2, we need to calculate the heat needed to boil the liquid. All right, so let's go back to those equations that we wrote down earlier. I'm just going to go back. Oh, there it is. Okay, so we're increasing the temperature of our liquid. So in our series of calculations here, that's number 3. And then we're also going to boil the liquid, which is step 4. Okay, so we're going to use those two equations where heat is equal to mass times delta T times specific heat of the liquid, and heat is equal to mass times heat of vaporization. Okay, so let's go back and write those down. Oh, I did not want to zoom. All right, so step 1, we're going to use this equation where heat is equal to mass times the change in temperature times the specific heat of the liquid. And then 2, heat is equal to mass times the heat of vaporization. Now, at the very end, we have one last step, step 3. Add the heat values together, which will equal the total heat. All right, so let's just plug in what we know and we'll solve for the heat values here. So number 1, we're going to calculate the heat needed to increase the temperature of our ethanol. So let's go back and look up the mass. So our mass was 15 grams, and then our temperature change was from 25 degrees Celsius to 78 degrees Celsius, and our specific heat is 2.46. Okay, we'll try to remember that, but we can always go back if we need to. Now, for our change in temperature, our final temperature is 78, and our initial temperature is 25. And then our specific heat is 2.46 joules per gram degree Celsius. Okay. Now I'm just going to simplify our change in temperature there. So 78.0 minus 25.0, I get 53 degrees, but I am going to take into account that both of my values here end in the tenths place, and we are subtracting. So we want to take into account the last place value, or the last decimal point there. So remember, with addition and subtraction, we can't be more accurate than our least accurate measurement. So whichever number has the smallest place value at the end, that decides our final answer. So we'll write 53.0. Okay, so let's figure out how much this is. So we've got 15 times 53 times 2.46. All right, so I get 1955.7. Okay, so 1955.7. Now, remember, we always want to take sig figs into account. So we were multiplying everything, which means we want to limit our answer to the least number of sig figs, or our least accurate measurement. So how many sig figs does 15.0 have? 3. So remember that last zero there is significant. It's after a non-zero digit and a decimal. What about 53.0? How many sig figs does that have? 3. And what about 2.46? 3. Okay, so that makes it easy. We just need 3 sig figs in our final answer. So I'll underline those first 3 digits. And then what about our unit? What's our final unit here? Joules. So grams will cancel and degrees Celsius cancel. So we get joules. Oh, didn't mean to do that. All right, so let's figure out what our answer is with the correct number of sig figs. So there's a couple of different ways we can write our answer. We could put in placeholder zeros, or we could write in scientific notation. All right, so in this case, we're dropping the 5 and the 7. So we'll write 1, 9, and then the first digit we're dropping is a 5, so we're going to round up. So we have 196, and then I'm going to put a placeholder 0 in the ones place so that we still have 1960. And then our final unit is joules. Or we could write this in scientific notation. So remember, our coefficient needs to be between 1 and 10 or equal to 1. So we'll write 1.96, and that gives us 3 sig figs. And then we have to multiply by a power of 10 to show the magnitude of the number. So let's let's figure out how many times we have to move our decimal point here to get to 1.96. So that's 1, 2, 3 times. And this is a larger number, so our exponent is positive. So 2 different ways to write the same number. Either way is fine, as long as you have 3 sig figs. All right, step 2. So we are going to multiply the mass by the heat of vaporization. So let's go back and look up the heat of vaporization. So that is 841 joules per gram. All right, so let's plug that into our calculators. Okay, so I get 12,615. All right, now how many sig figs should our answer have? So we already said 15.0 has 3 sig figs. What about 841? There's 3 non-zero digits there, so that also has 3 sig figs. So we're going to limit our final answer to 3 sig figs. And what about our units? What's our final unit? Joules. So grams cancel, and we're just left with joules. Okay. Now, again, there's 2 different ways that we could write this value. So we could put some placeholder zeros in. So let's see, we're dropping the 1 and the 5. So we would write 1, 2, 6 because we don't have to round up since our first drop digit is a 1. And then 0, 0. And I'm putting those 2 zeros there in order to make sure I still have 12,600. Or we can write this in scientific notation. So our coefficient would be 1.26. That's in between 1 and 10. And we have 3 sig figs there. But I do want to take into account the magnitude of the number with my power of 10. So in this case, I'm going to put an invisible decimal at the end of my number. And let's see how many times we have to move it. So 1, 2, 3, 4 times. All right. All right, so now the last step, we just have to add those 2 numbers together. So we're going to add 1,960 joules to 12,600 joules. All right, so I get 14,560 joules. Now remember sig figs. So we said we have to have 3 sig figs. So we're going to limit ourselves to those first 3 digits. And again, remember we can write this with placeholder zeros or in scientific notation. So we're dropping the 6 and the 0. So we have 1, 4, and our first drop digit is a 6, so we want to round our 5 up to a 6. And then we'll have 2 placeholder zeros there. Or, again, we can write this in scientific notation. Okay, so that was a pretty long problem, but hopefully it shows how we can utilize those different heat equations and figure out how much heat is needed for different parts of that heating curve. So whether we're increasing the temperature of a state of matter, or if we're boiling or melting, etc. Okay, so overall, we need 14,600 joules of heat in order to increase the temperature of our liquid ethanol to its boiling point and then boil it. And here are the solution slides if you want to look at those later. And now I encourage you to go over this problem on your own. It's multiple choice. So you can double check if you got the right answer, but I also included the solution slides so you can double check your work. So in this problem, it states when a volcano erupts, 175 grams of steam at 100 degrees Celsius is released. How many kilojoules are lost when the steam condenses then freezes at 0 degrees Celsius? So you might have to look up a couple of values, and those will be in the Chapter 3 slides. So for instance, you might have to look up the specific heat of water, or maybe the heat of vaporization of water. But again, those are all in the lecture slides. All right, so I will see you in the next video. This is actually the end of our Chapter 3 section for Module 2. So we went over matter in previous lectures, and in this lecture we talked about heating curves and cooling curves. We've also talked about how to calculate heat based on specific heats and mass and temperature changes. All right, so in the next video, we'll start the next set of chapter sections, so that will be from chapter 4. So I will see you then.